modeling portal section time history analyze SeismoStruct tutorial. Before you watch this tutorial, you should have already gone through the time history analyze individual assignment and have a better understanding about the method we use to conduct time history analyze hand calculations. You should also know the assumption we made in this section. Besides, you should also have watched the GSA tutorial in these sections, since the operation procedures shown in here, this tutorial, are similar to the approaches implemented during the GSA tutorial. Okay, so for this tutorial, you should be able to learn how to conduct a linear time history analysis in SeismoStruct. So before you start building your SeismoStruct model, it's recommended that you create a folder where you will save your model. Since when you carry out your analysis, a number of output files will be generated, and it's best to store all these files in the same folder. So to begin with, let's have a look at the SeismoStruct window. And here is the toolbar menu. Here is you can change the analyze type. Here you can select preprocessor, processor, and postprocessor. Here, right now it shows the preprocessor detail. Okay, so first we will need to create a new file and save it in the folder. Time history analyze and save it. Okay, then we should select the analyze type as the dynamic time history analyze. After that, we need to select relevant unit. Go to click on this U symbol from the toolbar menu, and select the length as meter, the force as kilonewton, so that we get the mass or turn the stress of kilopascal. If we change it to millimeter, this unit will change. Then we need to edit the analyze setting, which is click on this code well from the toolbar menu, and first click the program default, then go to analyze tab, unselect include geometric nonlinearities, and select run with linear elastic properties. Then we go to the integration scheme, click new mark integration scheme, and click on damping, use ready damping. And for the period of mode 1, that will be the fundamental period. In this case, that will be 1.0 seconds minus 0.05, so that gives us 0.95 seconds. And damping ratio is set as 5. For mode 2, that will be the fundamental period plus 0.05 seconds, that will be 1.05 seconds. And damping ratio is 5%. That is okay. Then we need to populate relevant info in all labs from left to right in the preprocessor area. So the material, first you should add general material, give a name as concrete. Elastic. And choose the material type as elastic material. The modulus of elasticity should be the same as what we have used in the individual assignment. So that should be 28,000 megapascal, so 2.87 kilopascal. And the sag weight should be 0, since we need to use the zero density material. And thus, then we have defined the material. We go to the section. We add new one, which is square, cross, section, and section type that will be defined as rectangular solid section. Material is the concrete elastic. Since in the assumption we use 500 millimeters by 500 millimeters elements as a column, so here in the dimensional unit of meter, we use 0.5 meter by 0.5 meter. Press OK. Then we go to the element classes. In the element being column element type, we add new one, which gives the element class is beam. Element type, there will be elastic frame element. Use square cross section, so we don't need to specify the value here. Ensure the damping is set as none and click OK. Then we also need to add the mass element, so we add one, rename as mass, and element type will be lumped constraint mass element. And the value in mx, the reason for why we import value in mx, you should understand that. So that's the value we calculate in the individual assignment will be 44.373 ton, and others is set 0. That's okay. Then we have defined the mass. Next thing we should do is to define node, and similarly to what we have done in GSA, we define two nodes. The first one is 0, 0, and 0 in x, y, z direction, and choose the structure node type as structure node, and node 2. So x, y is also set at 0, but y, z is 10 meters. Click OK. Then we go to the element connectivity. Here. And we press add. Here, give an element name as the beam. Element class is beam. Node 1 is N1, node 2 is N2, so you can see that in the right hand, the preview window. Okay. And we also need to define the element orientation. Actually, is rotate angle is 0. Then we also need to add another element, which is the mass. Class with the mass, and we want it to locate it at node 2, so we select N2. I can zoom in here. Okay. That's okay. Then we have the mass element. Go to restraints and select N1, edit it with string all because we want to fix at bottom. For N2, string all, but leave x directions unfixed because we want to see its behavior in x direction. Then we go to the time history curve, we create a new one, give the name as base acceleration. And description is also base acceleration. For the load curve, we do the same thing what we just done in the GSA, which is to copy the value here, that. And paste it in here. Then we can see the load curve diagram, which is the load factor versus time. That's okay. And we also need to add the time history stage. So for the end of stage, there will be the end time of this record. There will be 16.26 seconds. And the steps should equal to the overall time over the time step. In this case, there was 0.005 gives 3,252. So there is 3,252 steps. That's okay. Then we need to apply loads here. First, we add a new load, which is dynamic time history load, and the list will be the N1 because it's at base. It's the base acceleration. So direction is x direction, type is acceleration, and curve multiplier can be just 1.0. Curve name is base acceleration. Press OK. And then we need to define the analyzed output. Ensure that frequency of output is 1. You select the relevant displacement. Direction is set in x because we want to observe its behavior in x direction. And we also need to click both N1 and N2. We don't need to use mass. And then we can go to the processor and start to run. Before, it will mention that you should save the file, and yeah, you should save that in case there is a crash during this analysis. So this model this record is a bit short since it's just 16.26 seconds. However, if you encounter much longer period, for example like 30 seconds or 16 seconds, even more, then it usually takes a much longer time for the processing process. In the meantime, you can have a look at the model just built in the SeismoStruct and wait for the result to show up. And after we get the result, we can compare it to what we get from the hand calculations and you choose A. Yeah, since it's going to be at 16.26 seconds. Okay, the analysis has finished. You can go to the post-processor and click on the global response parameter. Here, select displacement. Base node is N1, so we can have a look at the diagram of N1, which is just straight line. For N2, yeah, there's a curve, so we click the values. We copy all and go to Excel. Paste it and copy our selection here. Paste it at here. Similar things for the velocities and accelerations. And first of all, the velocities, you should click the relative value, which is N1. If you don't click that, you can see the N1 actually is not straight line. So let's do that. And N2 will be a curve, so let's have a look at this value. Copy all and paste it in Excel. Copy all the values, paste it in here. And then for the accelerations, you can't just use the relative value, so what you should do is click on N1 and N2. And you need to do the process by yourself in Excel, which is to use N2 minus N1 and get the results. So by doing that, you can get the results for displacement, velocity, and accelerations, and you can compare these results towards the GSA and hand calculations. So that will be all for the SeismoStruct tutorial in section time history analysis.